Hello, Augies Worldwide. I'm Dave Casler, amateur radio call sign KE0OG. Today's question, or rather series of questions, come from Pat Davis, KQ4BRW in Micanopy, Florida. One of those has got to be right. Pat has been involved in a local group, and she sent a couple questions here. First question had to do with proper height for NVIS antennas. Then the other explains a little bit more about her situation. It's quite interesting here. Our group is MERT, Marion Emergency Radio Team, at Marion County Sheriff's Office. Okay, the first thing right off the bat, I commend Pat for doing this in coordination with the served agency. Independent emergency nets don't really do anybody any good. You need to have a, quote, served agency, in this case the sheriff's officer. It says, we staff school shelters during hurricanes, which happen quite frequently in Florida. And some of us are also in the hospital emergency communications who staff the 6 hospitals in Ocala, Florida. We've been having training over which style NVIS is best and which can be put at our houses for reasonable cost and which has the best SWR in 40 and 80 meters. If the grid is down, we would need to get voice and WinLink ICS 213 messages to Tallahassee, which is the Florida state capital, roughly 200 miles away, and that would work on 40 or 80 meters. At our EOC, we were practicing setting up an ex-military style NVIS antenna, which has about a 15-foot pole in the center with 4 wires running out of the top in a neck shape. I've seen pictures of these weird antennas. 2 are for 40 meters and 2 are for 80 meters. We would have to put up that right before the storm hits. And also, if the grid goes down, my husband and I would not be able to contact other members of the EOC using VHF since we were about 35 miles away. Well, that would depend on the height of the tower. Our VHF UHF antenna is Yagi, about 25 feet high. Our current HF antenna is about 25 feet off the ground from tree and is 92-foot end-fed, running mostly parallel to the ground. That's an odd length. Most of the other members live in gated communities with limited space and HOAs. Okay, there's a lot of questions in here. First of all, the 2 organizations to deal with for ham radio emergency service are ARES, the Amateur Radio Emergency Service, which is organized by the American Radio Relay League. The other is RACES, Radio Amateur Civil Emergency Service, which has some subtle differences from ARES, but frankly, people who are member one tend to be a member of the other. Now, the whole point about this, in preparation for an emergency, you have to know several things. One, what's the technical underpinning of all this? How are you going to communicate? What frequencies, at what time? Where do you go to meet? How can you get communications across a variety of spectra? Would it perhaps be a good idea to incorporate the GMRS radio service with this too? All questions that you answer with practice. The second point is that you have to decide how the net is initiated. I mean, the wind might be blowing. At what point do you open the net and keep it up for the duration of the emergency? Because if somebody doesn't know that the net is there, they're not going to be contributing. Third, there has to be all of the protocols that you will follow, what types of messages you will do, how you will do them. This requires not only learning the appropriate ham radio, but also the appropriate FEMA documentation on the operations in emergencies. There's a very definite way of doing communications in emergencies, and you want to do this right. With that, let me go through something here that I actually put up just for you guys. I gave a talk at Pacificon in October. It showed a series of graphs for how high an antenna was for best NVIS performance. So now let's take a look at those charts. We're looking here at a series of charts I presented in Pacificon. It started out with the dipole and ends up with good ways of creating an end-fed antenna. The dipole. A dipole is simply an electrical half wavelength, okay? It can be center-fed, it can be off-center fed, it can be end-fed, okay? You can bend dipoles. You don't have to have them running in a straight line. You can get, here's a side view of an inverted V, or if you look at down from the top, maybe you need to stretch those legs in different directions. You can also droop the ends. Now don't roll them back because that capacitively couples them and shortens the antenna, but droop them straight down. Here's a quarter wave with verticals where you feed it here and here, okay? Now the formula assumes a velocity of propagation in wire of about 0.95, and that means the actual velocity is 0.95 times the speed of light. This is the standard formula. Length of a half wave is 468 over f in megahertz. But then add a couple feet so you can make it longer or shorter as needed. Now it is true that element thickness very slightly affects the resonant frequency, as does the type and amount of insulation, but it'll only be a few inches, so if you just make it a couple feet shorter than this, you can pick it up. In terms of shortening antennas, a too short antenna is capacitive, so you need to add inductance if adding length is not an option. Such inductance is referred to as loading. A too long antenna is inductive, so add capacitance, or better yet, just shorten it. Using lumped inductance or capacitance creates a higher Q antenna without going into the detail on that, but it narrows the bandwidth. Some practicalities: where do you get wire? Home Depot or Lowe's, buy in bulk. Copper house wire, THHN, stranded. I say stranded because, first of all, it has greater surface area, and second, it's just a well of a lot easier to deal with. By the way, number 12 or number 14 will take all the way up to legal power. You can wrap insulated wire back on itself as part of tuning. Where to get the insulators? I go at Murdoch's, Tractor Supply, your local farm store, and get electric fence insulators. Where to get the masts or poles, I've got a separate presentation on that. This is an example of the wire that you can get. Notice it's gray. That makes it hardest to see. Here's an example of an insulator. This is from Tractor Supply Company. Now, in terms of multiband antennas, do you want to do a trap or a fan dipole? I recommend fan. Traps can be loaded to shorten an antenna. It will also affect antenna bandwidth, and I've got a rather extreme example of that coming up. The fan can be full size, subject to tuning, or hybrid, and as an example, the Alpha Delta DXEE, which is off center. You can go off center fed, you can go end fed with these. This is the Alpha Delta antenna. See, you've got 3 antennas in a fan configuration, and then here's the 20-meter section, then a trap, and a very short section for 40 meters. The reason it's so short is because the trap also acts as a loading coil on that frequency. Now, the problem with that is that it's a lumped inductance, so it will narrow the bandwidth, and this 40-meter section will cover half of the band. And you can pick which half you want it to cover by how you do final tune-up. But the fact of the matter is that you cannot do FT8 and voice on this thing from the same antenna. Now, here's another antenna that my assistant and I built. This is a homebrew fan dipole. See, there's a 10-meter element, a 20-meter element, 40-meter element. We just use plastic pipe to do these. Okay, now let's look at the ideal dipole radiation pattern, looking at it from the side. This is a standard dipole. It's a half wavelength long, half wavelength high. It has a gain of 6.82 dBi, meaning over an isotropic. The green dot, it's also over here going this way too. The elevation at the center of the beam is 33 degrees, so that's this line right here. Okay, But note, here's 5 dB down, not quite an S unit down, and you can go from there all the way to there. So you can get pretty broad coverage. Now, what happens when you make it taller than this? You start to build up a lobe here, which eventually bifurcates into 2 other lobes. This is optimal for getting your power spread evenly over a nice wide space. So here is a antenna. It happens to be made for 80 meters, but these scale. The scale here is that the height is only 8% of the wavelength, 80 meters. Okay, this is a very low antenna. It radiates straight up, although notice here, you're about 3 dB down here and about 3 dB down here. Okay, now that's a pretty wide area, so it covers about 45 degrees. When you're looking at NVIS, you want near vertical incidence skywave propagation. You want to be able to talk to stations that are like 45 degrees off. Okay, so let's take a look here where we go to 0.12 lambda. Notice it's still going straight up, but in our first one, the gain was 9.31 dBi. Here the gain is a little less, 8.78, but it's wider. Okay, so there's always a trade-off. Here again, we're pointed straight up. This time 8.35 dBi max, but with a wider distribution. This may be a little too wide. If you think that, here is one that is at 0.2 lambda. Okay, here's 0.24, which is nearly a quarter of a wavelength, which on 80 meters would be 64 feet. At 40 meters would be 33 feet. Now, if we get it any higher than that, we start to lose our upward stuff, and the band starts to come mostly in that direction. But look how big an area it covers. Let's go down 3 dB. Yeah, 3 dB over here. You've got a tremendously large area of radiation. Here we go to 0.32 lambda, a third of lambda. We start to lose a little up, but we gain again coming down. So the trade-off is the higher you go, the less goes up and the more goes out. Okay, here is one at 0.4 of a wavelength. We've seen this. Here's 0.44. Notice now that we're starting to get into the classic lobe pattern. Here's 0.48. We are really in the classic lobe pattern. Note that the 3 dB point here is about 15 degrees. So doing pretty good. Now if you come down to just over a half a lambda, you'll note this getting just a little bit flat in here, because if you go up higher than that, 0.56 of lambda, note that that's lambda, not half lambda. Okay, we start to create a third lobe, and it's sucking power away from the others. We've got still a 0.88 dBi load out, showing that this lobe is starting to grow. As it grows up, this will bifurcate, okay? And then what ends up with, you've got a very sharp null coming in this way. If you've got a signal coming in that way, you could miss it. It's 25 dB down, okay? Okay, so Pat, you and your group have been talking about the right height for your NVIS dipoles, and you've discovered in this presentation you've got a wide range that you can use. Actually, in NVIS, instead of going straight up, you want to go somewhere within an area like this, and the other station has to have a similar antenna so that it will receive what you're transmitting. But you can do some really marvelous things with NVIS. So generally, NVIS is on 80 at night and on 40 during the day. Those are generalizations. You should have several frequencies that you try. You might look at a concept called automatic link establishment. This is used by people for emergency services. It's not common at all in the rest of ham radio, but it's when you try to put a link together that is between cooperating entities in terms of finding and keeping a good open frequency. So there you have it. That's a lot of information about NVIS antennas, how you can pick the one you like. Generally, there's a range in there that gives you pretty good performance, okay? So if you'd like to help this channel thrive, become a member. You can do that right on YouTube, or send me a super chat, or you can go to patreon.com/KE0OG. Lots of different things. Until we next meet, 73.